All righty, folks, how y'all doing? We are back and we are talking about series and sequences. So essentially, we're dealing with this idea of order, of some sort of pattern going on here. And a sequence is essentially, it's a function whose domain is a set of positive integers. It's a bunch of entries and items. So as we're going through and looking at this, all we're doing here is when you're dealing with a sequence, you're going to be dealing with two things. First of all, this idea of n. That right there, that's called the term number. So it lets you know what number we're dealing with here. And then the next one is this part right here. We call that a sub n. Sub as in subscript, a sub n. That is the term value. So sequences are dealing with a set of terms in some sort of pattern, and it's our job just kind of deal with it and play with it a little bit. Some of these things will come up in both Calc AB and BC. We'll be getting into some stuff that we'll get into AP Stats later on at the end of this chapter. But for the most part, this is it's kind of an interesting idea. Things we used to teach in a normal integrate or algebra 2 class. They're not there anymore, but it is important that you guys know it, like I said, to get ready for AP Stats, AP Calc. Also, just for some things that will pop up on your SATs as well. So what we're asked to do here is we're going to write the first 5 terms of this particular sequence. So in other words, a sub 1, that means this a sub 1 is read as the first term value in my sequence. So I want to know what the first term is in my sequence. So if I write it out here like this, and all we're doing is we're just evaluating our term rule for this particular sequence. So -1/1, that is -1. So our first term in our sequence would be -1. A sub 2, we're going to just, so this will be the second term. So a sub 2 is the second term value, or the second term in our sequence. And we have to figure out what that term is. So we plug 2 in for n, and we get 1/4. So in this particular sequence, the second term is 1/4. A sub 3. So we have -1⁵ and 2 cubed. So -1⁵ is -1, 2 cubed is 8. So that means our third term in our sequence would be -1/8. Oh, I lied. I plugged in the wrong thing, didn't I? Oh my goodness, I just realized that. Let's fix that real quickly here. That should be 3 squared. There we go. How about -1/9? That might be a little bit better. And a sub 4, that'll be the fourth term in our sequence. So -1⁴ over 4 squared. So that'll end up being a positive 1/16. And you kind of see us going back and forth between positive and negative, all these different squares. And a sub 5 would be the fifth term in this sequence. So -1⁵ all over 5 squared. And we end up with -1/25. So each one of these is a term number or term value. I'm sorry, each one of these is a term value and its places where it is in the sequence. So this is our first term, and the value is -1. N is the term number, a sub n is the value. All righty, so what we're going to do here is we're going to go through and we're going to deal with some sequences just for a little bit. So let's clear this out of the way here. don't you guys take a look at these sequences right here and see what you can do with here. Same thing, you're still writing the first 5 terms in a sequence. So that hasn't changed. So why don't you guys see if you guys can write the first 5 terms in each sequence, and then we'll talk about it. So go ahead and pause the video and give it your best shot. All right, let's see how you did here. So the first term, you just plug 1 in for n. 5 times 1 minus 1, that would be 4. So our first term is going to be 4. Our second term, 5 times 2 minus 4, minus 1, sorry, that would be 9. And if you notice, this particular one looks a lot like y equals mx plus b. It's very similar to that. We'll probably talk about that in the next day or so. So 15 minus 1 would be 14. There's our third term. A sub 4. So 5 times 4 minus 1. That would be 19. And a sub 5. So 5 times 5 minus 1 is 24. So if you're looking at the terms here then, you notice that can go on forever and ever and ever. If you notice at the terms here, we see a pattern. We're always adding 5. Which if it's linear, it makes sense because that's what the slope is. Always adding 5. This kind of sequence right here, we say that it is arithmetic. And the reason why we call it arithmetic is because it is essentially just nothing more than repeated addition. And the phrase we'll use later is common difference. So, but it's repeated addition. That makes it arithmetic. Our next one here, if we plug these in here, so a sub, oops, I want to use blue on this one. There we go. A sub 1. So we have 2 times 3 to the 1 minus 1. So that's 2 times 3 to the 0. So 2 times 1, which is 2. So the first term in this is the term 2. All right, let's keep going here. So a sub 2. So 2 times 3 to the 2 minus 1. That would end up being 6. A sub 3. So that's 2 times 3 to the 3 minus 1. That would end up being 18. A sub 4. That's 2 times 4. 3, sorry. To the 4 minus 1. That's an ugly looking 3 there, isn't it? That would be 54. And a sub 5 is 2 times 3 to the 5 minus 1, which is 162. And again, this sequence goes on forever. If it goes on forever, we say it's an infinite sequence. A finite sequence is when we're only dealing with just a set number. So if I said the sequence is 5 terms long, 2 through 162, 5 terms long, that's a finite sequence. But these technically are sequences that can go forever because it hasn't been, there's no cap on it. So now if you notice on these ones, they're not repeated addition. Instead, it's repeated multiplication. And you guys can see that because you're dealing with exponents. exponential repeated multiplication. So that also has a kind of name to it. We call it a geometric sequence. Now, a geometric sequence, we call it that because it is repeated multiplication. And again, we will come back and hit these ideas here in the next couple of days. Now, one of the things you want to look at here is each of these values, you can plug a number in for n and get a term out. So if you can plug your term number in to get and end up with a term value, we call this an explicit sequence. These are explicit sequences. These are examples, and you'll see that at the bottom of your notes there, so you don't need to necessarily write that. You already have it. These are explicit sequences. And they're explicit because you plug a value in for n, and you get that term value. So you can figure out any term number you want just by plugging it in for n and getting that value out. That makes it explicit. All right. Now there's another type of sequence where it's not in terms of the term value, it's in terms of the term or terms before it. We call that recursive. So let's go take a look at some recursive things, and we'll see kind of what that looks like. So before I get into this, the most famous recursive sequence you'll ever deal with, and you guys have probably done it before, is this idea of Fibonacci, where if you have two numbers and you add them together, so 1 plus 1, you get 2. You add up two numbers, you get the next number. You add up the two numbers before, 2 and 3, you get 5. 3 plus 5, you get 8. I'm sure at some point in time, 5 plus 8, you get 13. I'm sure at some point in time, you've talked about this particular sequence. Now, this sequence is always started with defining it as 2. So we'd say, hey, let's let that first term be 1. And we're going to let the second term be 2. And then using the 2 that we know, we say, well, if we take those two terms, we can use it to find the next term. So say I wanted to find the third term. I would have taken the first term, which was 1, and the second term, which was 2, and I would have added them up to get the third term. The fourth term, I would have taken the second term, and I would have added the third term to it to get the fourth term, and so on and so forth. So in places of n, we would have said, okay, well, that's the same thing as you take the number that is 2 before it. So the term number that is 2 before it, or the term value that's 2 before it, and you're going to add it to the term value that is 1 before it. And this whole idea, this Fibonacci sequence is, like I said, it's the most common thing for what we call this idea of a recursive rule. Recursive meaning you define a term by the terms in front of it. So in order to do that, notice you always have to have at least one value defined for you. So this is our arithmetic sequence we looked at before. Let's see how it would look in recursive. So if I want the next one, a sub 2, this rule says if you want the next one, you have to take the one before it. So the term value before it is 4. And then you're going to add 5 to it. And you get 9. If I want the third term, the recursive rule said, take the number you got before it. So I got 9 before it. So I'm going to use 9. And I add 5. The nice thing about a recursive rule is you can see the repeated addition, or in this case, multiplication on number 2, happen fairly quickly. can see it kind of pop out a little bit earlier. A sub 4, I take the term value I got on a sub 3, and I'm going to add my next value to it. So this is called a recursive rule. Oh, apparently I got 14 and I want to change that to 13. Let's just fix that real quick. A recursive rule. Friends, why don't you pause the video and see if you guys can't do the recursive rule for the next sequence. All right, let's see how you guys did. Again, we start off with a value we know. So a sub 1 is 2. And the recursive rule says if I want a sub 2, I'm going to multiply 3 by the term before it. So 3 times the term before it. So the term before it was 2. So 3 times 2, and that would give me 6. A sub 3, I'm going to take 3, and I'm going to multiply by the term before it, so times 6, and I get 18. Some of you are probably going, why can't we just use the explicit rule? Well, we're going to primarily use it, but you need to have an understanding a little bit about what the recursive rule is. Recursive rules is kind of what determines and makes your spreadsheets work a lot. So it does have a lot of computer benefits to it. So 3 times the term before is 3 times 18. As long as you have just a kind of a good idea of what a recursive rule is, we're going to be okay here. So explicit, you plug a value in for n, and you get the term value you want. Recursive, you take the value or values before the term you want, use your rule to find the one you want. So recursive, you have to essentially count up. In recursive is that idea of recurring. So you see that recurring addition to get the value you want. Where explicit, you just plug in a number, you pop a number out. So next thing is something called factorial. This n factorial basically means we're going to count from 1. We're going to multiply all the numbers from 1 up. So if I want to do 5 factorial, that means I'm going to multiply all the numbers by 5, from 1 all the way up to that number. So 1 up to 5. And that would be 120. So you're going to multiply all the numbers from 1 up to that number. So just to make sure we have this idea down, friends, list what 3 factorial would be, and then go ahead and do that real quick. Let's see how you did. So 3 factorial means I'm going to count from 1 up to that number, so 1 up to 3. I just multiply them all together. So eventually, when we get to this idea of counting, or counting principles, that'll be in a few days, we're going to use this idea of factorial quite a bit. But it is something you're going to see on your SATs. You're not going to see it in calc. You'll see it a tiny bit in stats, I guess, but on your SATs, you'll see this exclamation point pop up, and you need to make sure you just have a decent idea of what's going on. All righty, let's keep going here a little bit more. Now, this is something that we are going to use a lot in future math classes, this idea of summation. What this idea of summation or sigma notation means is you're going to add up all the terms from 1 to n. From 1 to n. This number right here, this is called your lower limit. I stands for index. I is not the square root of negative 1. It stands for index. N is your upper limit. So we're going to, and I'll show you how this is going to play out here in a second. Upper limit. And notice we have our sequence rule right in here, which will give us our term value. So how does this work? We're going to count from 1 up to 7. So I'm going to end up with 7 terms. And this sigma notation, this summation notation means I'm going to add up 7 terms. I'm going to add from all the values from term 1 to term 7. So in other words, my first one says, if I plug it in, I'm going to plug my term number into my rule. So 3 times 1 plus 2. So that would be my first value. And I'm going to keep doing this for all my values from 1 up to 7. So let me just kind of write all this out here, and then I'm going to show you a little bit, try to organize a little bit so you can see it a little bit better. But I don't want to have to go back through all these colors. So what is going to happen here, friends? When we're dealing with sigma notation, I'll give you a hint. I just got done dealing with sigma notation with my calculus friends when we were talking about something called a Riemann sum, which you guys will find out about next year. All right, so we're starting with our lower limit 1, and we're counting up 2, 3, 4, 5, 6, 7. And you'll, if I kind of separate it with parentheses here a little bit, so there's my first, plugging my term number in to my sequence rule to get my term value. There's the next one. I'm plugging all my indexes from 1, my lower limit, up to my upper limit into my sequence rule. So I'll figure out what its term value is. And the summation says take all those values and literally just add them all up. So if I add them all up, I got equals 5 plus 3 times 2 is 6 plus 2 is 8 plus 11. And notice we're going to have 7 values because I went from 1 to 7, 7 values. 14 plus 17 plus 20 plus 23. So there's all my values, and the summation just says add them all up, and we end up getting 98. All right, friends, why don't you try the next one? Don't do that last one yet. Why don't you guys try this second one? See what you guys come up with. All right, so I'm going from 2 to 5. That means I'm going to be evaluating this when I is 2. I'm going to evaluate this with my next I. I'm counting up from 2 up to 5. So now I have a 3. All a summation notation is, you're just literally plugging numbers in so you can sum, you can add up all the numbers. 4 and 5. So we have all our values now. Hopefully you guys got those 4. And we're going to add them all up here. So 3 times 2 squared, that's 12. Plus 24. Still one of my favorite shows that has been on. 48. If you guys haven't gone back and watched all the 24s, that's a good show. Plus 96. And we end up getting 180. All right, so let's take a look at this last one. Notice I have an infinite number of terms. This is an infinite sequence where the 2 before were a finite sequence because they had an ending value. These are finite. These are finite because they had an ending value. This one is infinite because it doesn't. It goes on forever. Its ending value is none because it's infinity. So this says I'm going to plug in all my numbers from 1 to infinity. Well, friends, I don't think I have to plug in all my numbers from 1 to infinity. Sometimes we can see a pattern. So if I plug in my number, there's my first one, 1. Let's just plug in a couple and see what happens. 3 to the 10 or 2. And I'm going to write out maybe 5. Maybe that'll be good enough to help us kind of see what's going on here. Dot, 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 and just going to keep going on forever and ever and ever. So I got 3, I got 4, and I got 5, like that. So 3 over 10 to the first, that's 3 divided by 10, that's 0.3. 3 divided by 100 is 0.03. 0.003 plus 0.0003. Do you guys see a pattern developing yet here? 0.0003 or 0.0000003. And we can keep going here, and all of a sudden you see all these numbers. If I start adding them all together, it's just a whole bunch of threes. Dot, dot, dot. And friends, if it's 0.333333, isn't that the same thing as 0.3 repeating? And 0.3 repeating is the same thing as 1/3. So sometimes sequences can come to mean something else. It's kind of crazy if you think about it. I kind of like the beauty of this. If I were to add up an infinite number of terms, I actually get a value that equals 1/3. It doesn't go to infinity, it goes to 1/3. It's kind of a cool little symmetry to it, a cool little beauty to it. I kind of dig it a little bit. Well, this idea of adding up and summations and this idea of sequences going on forever, one of the places that's found most often is in money. So we're going to talk a little bit about money. We have this a sub n equals p times 1 plus r over n times n minus times t. And we can use this compound interest to help us figure it out. By the way, a lot of banks will use something called continual compound interest, which we won't necessarily get into, but it's still all the same things. And if you get into continual compound interest, that is a sub n equals the amount you have is p times e rt. So p, r, and t all say the same thing, but realize this e is this value we talked about back before, where e is actually this number 2.718281828, 2.718281834, dot, 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 dot. It's that whole Euler number thing. It's one of our 5 fundamental numbers. Now, we're not going to necessarily get into that, but realize that could potentially be there a little bit. Okay, so that's another type of compound interest. We're just not going to deal with that one. Anyways, so we have this formula. P stands for the principal, or the beginning amount of money. R is the percentage rate is written as a decimal. N is the number of times compounded per year. T is the number of years. A is the money you're going to have when you're all said and done. So friends, take a look at this problem we got here. See if you guys can use this formula, this compound interest formula, to determine how much money I would have in my account after 7 years. Go and pause the video and give it a shot. All right, let's see what we have here. That'd be our P value. So P is 3,200. Here's my R value, but remember, it's got to be as a decimal, so it's not going to be 8, it's going to be 0.08. Compounded monthly, that means the number of times per year is going to be 12. And my T value is right here, 7 years. So if I wanted to evaluate this thing to figure out how much money I have, I'd have 3,200. So I'm starting with $3,200 in my account. It's going to compound, so I'm going to keep continually adding to it every single month. That's a repeated addition idea. Although it's going to be exponential in nature, so it's more geometric than it. Well, it is geometric actually. It's not going to be arithmetic. So it's 0.08 is my decimal. It's going to be 12 times per year. And then I have 12 times 7. So friends, you literally just plug that into your calculator and you can figure out how much money you'd have after those 84 different periods. So 12 months, 7 years, that's 84 different compounding periods. And you would have $5,591 and 75 cents. So almost double just by leaving it in your account for 7 years. Well, friends, that's just a quick introduction into sequences and series. We're going to be playing with this idea for the next 3-4 days. So have Have a great evening. We'll come back to class tomorrow and we will talk a little bit more about it. Take care.